Ladies and gentlemen, what if I were to tell you that we could actually close out transcendental numbers, pi, e, and even the golden ratio using a single function that I believe actually helps unite mathematics? Because we're not just talking about closing out irrational values to a whole valuation, it's also about being able to bring in perfect numbers to help us with the process and even embed our entire counting system starting with 0 on the decimal level. It's just absolutely beautiful. I think that when you see what I'm about to show you, you'll begin to understand how connected it all is, and it connects synergistically too. But I've been having a lot of trouble. I've been having unbelievable hacking for almost 500 straight days. And it's not a type of mundane hacking. It's a type of high sophistication that makes me question what kind of tools are being used to get to this channel. So what I'll do is I'll post a follow-up video and showcase how these hacking events occur and how it's done through devices that have every single internet disconnected, yet the device acts like there's like a poltergeist messing with the calculations. Oh, did you see that? The last video was unbelievably difficult to edit. I had to create over 100 project files to make sure that I always had a project file that wasn't messed with. And the process probably took 10 times longer than normal. So without getting too much into detail into the unpleasantries of why this is happening, I was unable to finish my own calculations, but I want to encourage the audience to take these equations and try it out yourselves. It's amazing. It really took my breath away. So without further ado, let's get on with the show. All right, ladies and gentlemen, this is a really exciting episode. Not so exciting with the hacking if you just caught the intro, but if you're not into mathematics and you're wondering why should I even be watching this video? Well, first of all, it's because the equations that I'm about to offer are actually quite simple, almost shockingly simple. It's something that you can put into your calculator. So if you have mathematics teacher, mathematical friends, or you just want to impress your academic relatives, these are equations that you can literally plug into your calculator and impress your friends, so to speak. It's also novel construction. Now, I'm not entrenched in mathematical academic papers, so I can't promise you that everything is going to be novel, but it's novel in the sense that I didn't use artificial intelligence. It was just me, paper and pen, figuring out patterns that, having taught SAT and ACT mathematics before, this was something that I've never seen before, and it was shocking. But even better than shocking, it was beautiful. It was synergistic. It connected in ways that, to be frank, it just seemed almost impossible, like it's too good to be true. And I do apologize about the creepiness of the numbers, but we do have a few characters that are going to show up on these equations. We have 7 is going to be our cool protagonist, 15 is going to be kind of like a supporting character, and then we have 0, a little grumpy 0 there. He kind of evokes the impossibility and the difficulties of trying to relate with certain equations where we fall into that singularity issue of having to divide by 0. And I'm going to try to offer you a second way of looking at the form that might give us an escape away from grumpy 0. And if you see this little trophy with the underdog story, well, a lot of mathematicians talk about perfect numbers as being something that is, well, symbolic. But I intend to show ways to use perfect numbers that become significant. Of course, a lot of this has to be peer reviewed, but I do believe, based on a lot of the logical structures that were used with some of these equations, that perfect numbers aren't so symbolic, but are actually rather important when you have to evoke numerical associations that don't have a middle value. For example, binary systems. And the rationality that we're discussing is to a high limit where the calculator calculates it to be a whole value, but I can't promise you that to the end of infinity, it's gonna be perfectly resolved, but nonetheless, I do think it's rather significant. And 2/9 is the engine that we're gonna use. Now, if you take any number and you divide it by 9, It's basically an ongoing sequence of the exact numerical number on the decimals. So 2/9, for example, would be 0.22222 to infinity. And of course, we got our architect, the golden ratio. And I see the golden ratio as kind of a holographic codec that allows us to map the universe, and it kind of scaffolds the universe in both a micro and a macro connection, allowing a type of wormhole for mathematics. And in general, this is going to be a story of how we get irrational values to become rational. It has beauty, it has connection, and it has synergy as well. So we're going to be taking pi, e, the golden ratio, and its other roots, which is also called the negative conjugates, and we're going to basically harmonize it in this really weird looking triangular guitar, but we're going to harmonize it to whole values. At least whole for what the calculator calculates, which is about 14 digits, floating points. And if you're unfamiliar with functions, generally it's when you see a f of x, it just means it's the output. So if we think about a function as a type of factory, let's say we're making shoes, x is the input, so we put the ingredients inside the factory, and the output, which we usually construe as y, but in this case, if you see f of x, just know it's the output of the function. So in essence, in this episode, I'm going to give you a brand new equation that's going to mix some of the irrational values, and I think it's a kind of a novel way to bring into rational evaluation, but to also evoke our very cool 7 character. In addition, I'm going to provide you the unifying equation that you can then use the variable of pi, and then I'm going to show you how to use very basic relevant modifications that will allow you to get it to a rational value, at least as is calculated from the calculator. We're going to use the same equation to use e as a variable, and then I'm going to show you how we can actually embed our counting system starting with 0 to 10. And then the reason why I said this is synergistic is because we're going to actually use this same form that we applied for the f of pi to get to a structure that will allow us to find rationality with the f of v. So it's as if the f of v and f of pi are working together to get a rational evaluation. And probably one of the most amazing things, something that I never expected mathematically, is going to be what happens when we plug in the golden ratio. Because what gets the golden ratio out of its rationality is going to be its other roots. And this is really interesting because it's as if to say that when you define the golden ratio as its f of a, as its quadratic equation, which is a squared minus a minus 1 equals 0, that quadratic equation has 2 roots. And the roots stand for a type of polarity that happens within the structures or what can be implied within this quadratic equation. Anytime you have a squaring function, it can usually intake a negative form because negative times a negative is a positive. So when you have an a squared form, for example, x squared, if I were to say x squared equals 4, well, we know that both 2, which is positive, and a minus 2, both of them being squared, will result in the same evaluation of 4. And that's what I mean by having 2 different roots, just that the golden ratio is a little bit different because its roots is not similar at the coefficient level. The golden ratio is 1.618033. The coefficient level is this guy right here, and the decimal is this guy. So the other root of the golden ratio is going to be minus 0.618033, and I should put a dot here because this is ongoing. What makes the golden ratio's quadratic equation unique is that the actual equality that you see is not happening at the 1 where the coefficient is at, but it's actually happening at the decimal level. And although this might be a little bit tricky to understand right now, it's going to make a lot more sense as we go through this episode. So my intention is to make this episode very, very skin and bones. I want to get right to the topic. I want to give you guys the equation right away, but I do need to go over a few topics, including what is transcendental numbers, what is perfect numbers, and why is the golden ratio folding time, and what is the logic behind why this equation seems to be doing something that I claimed is seemingly impossible. So in essence, transcendental numbers like pi are numbers that are infinites. It doesn't end. Perfect numbers are numbers who have factors that outside of itself add up to the number itself. So the first four perfect numbers are 6, 28, 496, and 8128. Now 6, we can find the factors very easily. It's 1, 2, and 3. And we can see right away that 1 plus 2 plus 3 equals 6. Now, if we look at 28, we have the factors of 14, 7. You know what? I should have put it in the same order, but I'm going to go from highest to lowest from now on. 4, 2, and 1. And again, if you add those together, that will equate to 28. 496, we have 248, 124, 62, 31, 16, 8, 4, 2, and 1. And 8128, we have 4064, 2032, 1016, 508, 254, 127, 64, 32, 16, 8, 4, 2, and 1. And it's really important to note that perfect numbers, the reason why I talked about the potentiality of them representing a type of oddness for binary systems is because every perfect number is going to have at least one factor that's odd. So for 6, we have 3. For 28, we have 7. For 496, we have 31. And for 8128, we have 127. And it's also worth noting that these are also prime numbers. Now, in the last episode, we went over the reason why the golden ratio might be folding time. Now, this is a personal interpretation, so I want you to take it with a grain of salt. But the idea is that we have the quadratic equation of the golden ratio. Let's call this f of a equals a squared minus a minus 1. Now, that just means that when a squared minus a minus 1, when that equals 0, that the results that will allow this quadratic equation to become 0 means that the a has to either be the golden ratio, which is 1.618033 and ongoing, or it has to be what's called the negative conjugates, the minus 0.61803. This is a symbol of the golden ratio, so if you see this, just note that it pertains to the golden ratio. And the negative conjugates, you can actually acquire that by simply writing 1 minus the golden ratio. What that means is that both of these can be plugged in for a, and they will result in 0 for a solution. But it's really interesting because the golden ratio, if you do have a squared minus a minus 1 equals 0, then when trying to define 1 itself, we can just bring it over to this side. So then we have a squared minus a equals positive 1. If I were to reshift the equation, I could also write this as minus a squared plus a, and that would equal minus 1. But it's important to note that the golden ratio, when expressing the numerical evaluation of itself, it's either a true functioning form for 1 or minus 1, or it becomes, I guess I would say there's 3 constituents for 0. But because 1 or minus 1 is a two-part form, then in essence, when defining the golden ratio as being equal to 0, it kind of has 2.5 functions, right? Because we have a squared, we have minus a, and then we have minus 1 or positive 1, depending how you shift the equations around. But minus 1 or 1 can only be expressed with two functions related to the golden ratio. So it's as if it represents half of a function. So in essence, when you talk about the golden ratio representing itself in reference to 0, it's as if it's representing 2.5 functions. But there's something really interesting that's actually happening here, because minus a, although we can say that that's just the negative golden ratio, it can also be defined with the rotational dynamics, which means that if I were to take the sine of 306 degrees plus the cosine of 216 degrees, well, that equals the negative golden ratio. But it's only when we express the negative golden ratio can we then infer switching the numbers. So instead I would write, for example, sine of 216 plus the cosine of 306, and that, ladies and gentlemen, equals 0. But wait a second, isn't 0 a function? Wait, so if the rotational dynamics equals the negative golden ratio, and simply switching the numbers or the actual functions themselves result in 0, then isn't it safe to say that 0 is also an implied function of the golden ratio's own form? But here's where it gets a little bit tricky, because we can't actually technically define 0 as this dynamic until we've defined the negative golden ratio. But if the equation is a squared minus a minus 1 equals 0, the thing is, there's an orders of operation that we have to do, and a squared comes first. So if a squared gets expressed, then we can express either minus 1 or minus a next. So by the time that we've finished with a squared, we then have minus a and minus 1 to contend with. And at this point, we can then say that yes, this 0 now becomes a function, at least for rotational dynamics. It's as if it has 2.5 functions in 2 different moments in time. So I guess that's what I meant, that the golden ratio seemingly is folding time, which comes back to the concept of Ouroboros. But the reason why I'm showing the Ouroboros is because it occurred to me only after I did the mathematics that perhaps this math is not so novel. It's not that it's not novel today, it's that maybe the ancients knew about this. Well, it stands for a tail that's eating. That's actually the root meaning of the Oro and Boris, but the symbol of it is very interesting because it means a symbol for eternal cyclical renewal, but also something that consumes its own self. In the mathematics, if we are able to take a transcendental number and bring it to rationality in a way that seems like it's impossible, the logic is that it's because the number is self-reflectively eating its own infinity. Yeah, and this is going to be a lot more clear when I showcase the equation, because you'll see how the structure of the equation kind of inverts on itself as if the variable is allowed to eat its own infinity. All right, so as I promised, let's get right to it. I'm going to go ahead and give you an equation that's going to mix the golden ratio and pi into a form that's going to be, well, rational. And it's going to bring back our little 7 hero over here. So the equation is really 5 minus 25,255 divided by 5,045 minus the golden ratio minus 1 divided by 45. Now remember that 45 can also stand for 45 degrees, meaning that it's 1/8 of 360 degrees, accounting for a full circle, plus our 7 hero cubed divided by 10 powered by 7 pi divided by 10 powered by 6 plus the golden ratio divided by 10 powered by 7. And actually what I'm going to do is I'm going to bracket this off as red over here. So we have this section plus 7 cubed again, this time times 10 powered by 13. And then we're going to have minus 1/9 times 10 powered by 10. And so if I extend this bracketing like this, we're going to take that entire form, divide that by 10 powered by 15. And if you want to construe the golden ratio and you want to write it in your calculator, you can write the golden ratio as √5/2 plus 1/2. And that will get you that form if you want to just be able to plug it into your calculator. But all of this is going to equal 3.43. Effectively, the infinity that you see with the irrational evaluation of the golden ratio and pi gets canceled in this form. And what's interesting is that 3.43 returns back to our 7 hero, because what ends up happening is there's 2 ways you can write this. You can either write this as 7.5, which equals 3.5, minus 7/100. So that's 3.5 minus 0.07 to become 3.43. But another way that you can write that is you can just write it as 7 cubed divided by 100, because 7 cubed is 343 divided by 100 to equal 3.43. And I think this is just phenomenal because you're not only being able to mix the golden ratio and pi in such a way to get such a clean value with no decimals running. So it's as if the infinity of the irrational evaluation is being taken care of, but it's taken care of in such a way that it returns back to an evaluation that becomes significant to 7's presence. And that's a theme that you're going to see, that a lot of these equations are effectively using the nature of 7 to be able to evaluate it to a clean result. Now, if you're wondering what is the deal with 25,255 or 5,045, well, there are many ways that you can write this. I could write this, for example, 25,000 plus 255, but something that I find kind of interesting is you can actually evaluate this from a perfect number perspective. So, for example, let's actually start with our 15 character, right? Our Robin, if this is Batman. One way that you can write 25,255 would be to use 15, and we can write this as 15 squared times 10 squared plus 10 powered by 4 divided by 4, and that just ends up being 2,500, plus another 15 squared. So this is probably unnecessary. I could have probably just written 15 squared times 10 squared plus 1. But just to keep it simpler, I just kept it this way, but adding that by 5 squared plus 5, this entire construction, which is basically like a 15 construction, equals the evaluation of 25255. Now, remember that 5 is 1/3 of 15, and 10 is 2/3 of 15. If you recall, the a squared minus a minus 1 equals 0 golden ratio equation, when expressing to a whole evaluation of either 0 or minus 1, you're always having to use either 2/3 of the total equation, or if you evaluate it as a minus a, for example, being the sine of 306 plus the cosine of 216 degrees, well, that minus a would account for only 1/3 of the equation. And this is a property that I'll go over later on when we get more in depth, but the idea is that the golden ratio can kind of stand as a functioning count for these very important fractions that can be reapplied to the numerical forms themselves to create something that is nearly a purely 15 type of identity, so long as these transformations can be made. If you recall the perfect numbers, I could use 496, and I could, for example, say 496 plus 7 squared, which equals 545. If I multiplied this 545 by 10, that equals 5,450. And if I subtract that by 360 degrees, which is the numerical evaluation of the degrees of a total circle, plus 45, as we just discussed, is 1/8 of a circle, well, that becomes that 5,045 that we see over here. So effectively, we have a number that's embedding a 15 form system in another one that can be construed as either 5,000 plus 45, but there is a way to get there using a perfect number. And you're going to see that this is not the only perfect number that we can use on the next equations that are, well, kind of unifying, I would say. So if you want to know what, so I guess at this point, I'm going to write this unifying equation, and I'll showcase to you what it looks like graphically, because it's really almost shockingly simple, but the graph that it showcases has a type of asymmetrical inversion, right hand, left hand symmetry. So in a way, it kind of reflects not only asymmetry, not only an inversion across the x-axis, but also a type of symmetry and asymmetry at the same time. And this is where the Ouroboros concept is going to come into play. So the f of x of this equation equals 1 minus 2 over 9x cubed plus 1 minus 2x cubed over 9 plus 4.9, and I'm going to parenthesis that off to be able to then multiply that by 10 powered by 4. And it's really that simple. This equation, ladies and gentlemen, is going to unify the irrational values and help us find rationality and a synergistic interaction between the mathematical planes while actually utilizing perfect numbers and even embedding our counting system into the decimals of this. So if we take this equation and I apply it with the f of x and replace the x for pi, so it's basically doing the exact same thing. So I'm just gonna rewrite it over here as, and it's good to parentheses these off because sometimes the calculator will misread how you're trying to construe this. So that's not going to be rational quite yet, but we do get a result that equals 25.49285614885777. It's worth noting that 4.9 is also 7 squared, which equals 49 divided by 10. So there are various ways that you can construe some of these numerical numbers, but just wanted to showcase how 7 keeps showing up in our equations. So you're thinking, okay, that's not rational. Right, it's not rational yet, but if you do take this and modify it just slightly, all we have to do is then add this form to, again, we're gonna use our 7 divided by 9 times 10 power by 7 minus 1 over 9 times 10 power by 10 plus 20 divided by 10 power by 13. And then we're going to use 20 again, and I'm going to put a different color parentheses so you can see what's going on here. So what we're going to do now is we're going to take a 20 squared form, and it's going to be multiplying into this parentheses for 10 power by minus 7 plus 10 power by minus 10 plus 10 power by minus 13. And then we're just going to add one more form, which is going to be plus 1 times 10 power by minus 13. And ladies and gentlemen, all of this, so you take this equation and you just modify it with a simple modification over here. Well, it's not so simple, but it's relevant in terms of the numerical associations that we're using. And that becomes, amazingly, 25.4929. It basically cleans itself out. Now, 25 is just a quarter of 100, and we just went over how 49 is 7 squared, so 0.49 is really 7 squared divided by 100, 0.0029. It might look random, but we know that 360 degrees has 30 times 12. We know that 12 is 1/3 of 36, so that equals 12. And well, we know that 29 is just 30 minus 1, but I think a really interesting way of depicting 29 is by taking the golden ratio, we power by 7, add it to the inverse of the golden ratio, power by 7, again, we keep seeing that 7 showing up, and that equals 29, which means that if we were to take that 29 and divide it by 1,000, well, there it is. So another way of writing this is 1/4 of 100 plus 7 squared divided by 100 plus this construction divided by 10,000. That's it. That's our number right there. Okay, so here is our equation. And as you can see, it does have this kind of inversion to its construction. And that's what I meant by the Ouroboros. It's as if part of itself can be induced in a type of dynamics that is at least inverted in the numerator and denominator structures such that the variable itself eats its own self. So we just calculated that the pi variation of this equals 25.49285614885777. Okay, so this is the pi variation of this equation, first becoming this decimal evaluation, but with these modifications being able to clean out to 25.4929. Now, if we take the exact same equation and we use E instead, so instead of rewriting everything, I'm going to showcase it in the calculator screen, but effectively when we use f of E, the result becomes, meaning that we're just plugging in E for the x instead of pi, this becomes 24,254.8355743211. But this result is absolutely astonishing, because if you recall our initial equation that allowed us to find rationality by mixing the golden ratio and the pi formula, well, remember our 25-255 form? Look how close that is, which means if we bring back our 25, and this is what I mean by using synergistic interaction. So if by bringing back the 25-255 form, I can then say that 25,255 minus our f of v form, that's going to equal 1,000.164425678947. But here's the thing, if I take that form and I subtract it by 15208 over 100,000, and again I subtract it by, this time we're going to do 432, this is a number that we talked about in our earlier episode, plus our 45 again, and this time it's going to be divided by 10 power by 13, just so I don't have to write all the zeros. Amazingly, ladies and gentlemen, this is going to be 1,000.0123456789. Effectively, we've just embedded the entire counting system on the decimal while getting almost a near clean result with 1,000 by simply utilizing our earlier number. And 432, it's actually just 1.2 times 360, or another way of construing 432 is you can say 6 cubed times 2. Both of those are going to equal 432. We already discussed the 45 being 1/8 of 360, but what's up with 15,208? That seems kind of random, right? Well, we can actually use the perfect numbers to evoke that. So if you remember our 5045 form on the original equation, we used 496 to potentially construe that number in a specific manner, but this time let's use 8128. So basically 8128, the fourth perfect number, times 2, which equals 16,256. That number subtracted by 1,000 plus, again, returning to our 7 squared, minus 1, that equals 15,208. So these numbers, they may look random, but the forms that allows us to get back to them are very self-reflective. If you notice that we're not only using perfect numbers to establish them, but using 1,000, the 7 exponentiation, and the fact that we can embed our entire counting system starting with 0, I think is just absolutely phenomenal. But what happens if we don't want the counting system? Is there a way to just get a clean number, rational, no decimals? And yes, we can get it, but we have to use something that we already calculated, which is the f of pi. So if we were to take this number right here, write it as 2 8 ... But if we were to take the f of pi divided by 1,000, or excuse me, 10,000, and we add that construction to the golden ratio divided by 10, this is so self-reflective. This is where the synergy and the Ouroboros really comes into play here. I'm gonna eat my tail. So when we take the original construction of f of pi divided by 10,000, added to the golden ratio divided by 10, we're gonna get a small decimal. And all we have to do is add this form. We're gonna add that, so I'm gonna place this over here, and we're just gonna call this, I'll just call it f of pi and the golden ratio. So when we combine that, all we have to do is then add this we're gonna add this to 2 times 7 cubed. Now look how self-reflective these forms are. We're gonna, again, use that 20 form, only we're gonna power it by 4, and then divide it by 4, add that to 9 squared, and then we're gonna take that entire construction in parentheses, and we're gonna multiply it by 10 power by minus 6, and we're gonna add this to 5045. Once again, reestablishing that original 5045 that we used for the original equation. And I'm gonna run out of room here, so I'm just gonna draw it down here. But we're gonna add that to 3 times 100, so just 300, plus 15 squared. So again, super self-reflective. And this is the coolest part. We're then gonna use Ramanujan's number 1729, and 1729 will give you a tiny little decimal that, when taken into account with the E equation, well, as you can see from the calculator screen, that results in a perfect 1000. This is just phenomenal to me, to think that the f of E can not only create a counting system embedded into the decimal, but they can self-reflectively borrow from the pi construction to build the very decimal that wipes it clean to 1000. I mean, I don't know how to express it. I mean, I think when you see all these jumbled numbers, it's hard to depict the beauty of the mathematics. It's kind of like this, right? It's like you're seeing the equation, we get the pi, that's rational. We try the E, we get the counting system, we return the pi plus the golden ratio construction to then get a clean rational result of 1000. And now the question is, what happens with the golden ratio? And this is where it gets really, really exciting, because the golden ratio requires a lot less work. Let me show you what I mean. Since we have our equation over here, I'm not gonna try to rewrite everything because it just gets too long. But if we do the same thing for the f of the golden ratio, and this is the most amazing thing, I almost fell off my chair when I noticed this. So I'm just gonna give you the results. You can check out the calculator, how it's calculating it. But this becomes 59,061.9201000094. It's not clean, but what I find to be absolutely phenomenal, and I still am like flabbergasted by this fact. If instead of using the golden ratio, we use the inverse of the golden ratio, which can also be written as the golden ratio minus 1. Now, if you recall, golden ratio's other root is 1 minus. But if you write this inverse of the golden ratio, ladies and gentlemen, that equals 59,061. And well, I don't need to write the rest. I think you get it. It's the exact same numerical evaluation, or the exact same sum, f of x. In effect, we have two completely different evaluations that are inverse to each other when inputted into this function, resulting in the exact same numerical evaluation. And this is a superposition state. For all the physicists out there, this is really important to note, because the golden ratio, various ways of describing a superposition, and I'm gonna get to this in a second. But the main question is, how do we get this to be a rational result? Well, instead of using the golden ratio or its inverse to get the same evaluation, let's instead do the f of the other roots. Over here, let's try the negative 1 over the golden ratio. That equals 78,938.07989999907. Now I know it's hard to see right now, but that means that these two, if you guys hear the fireworks right now, I think somebody's celebrating, but that means that the f of the golden ratio or the f of the inverse of the golden ratio plus the other root of the quadratic equation, let's celebrate, ladies and gentlemen, that equals 138,000 clean. I'm so excited, I can't even write clean right now. There we go, clean. This is unbelievable. We are basically extracting the irrational aspect of the golden ratio synergistically while creating a superposition state that can intake either the golden ratio or its inverse to be added to the other roots or the negative conjugates as it's applied to the function, so that their additive forms can result in 138,000 clean. Is one other issue, and that is our grumpy zero. You see, the problem with this equation is that, as you can examine on the calculator, we don't have the ability to create an f of 0 because that gives us an error. But is there a way out? What if we restructure the formula by keeping it the same, but almost like as if we're interdimensionally shifting f of x just slightly by changing the parentheses, we can actually get that 0 to become 2 exactly. And why is this so important? It's because, as you see in the calculator, 2 can be expressed by the golden ratio as either the golden ratio plus its inverse squared, or we could actually write it as the other roots, which can also be expressed as 1 minus the golden ratio squared. Because this is a negative evaluation, if it's gonna square, it's gonna turn positive, which means that this, which is 0.618033, is gonna be identical to the negative form being squared, which means that we have another superposition state. So in other words, if we do re-establish this equation to allow itself to take in the 0 by opening up the parentheses, we can establish a new type of superposition that can utilize the golden ratio. I guess with the celebration and the lights turning off, this is it, ladies and gentlemen, we are done. But I just wanted to show you how incredible, how well connected, how beautiful the mathematics is. And please don't forget to share this, ladies and gentlemen. The hacking that's happening, the type of things that are happening in the background, it's just unbelievable. I'm gonna post a video to showcase just how elaborate, how sophisticated the hacking is. And that's why in the end, I wrote you in the outline, because I wanted to establish the connection not only with the mathematics, but being able to connect with you and hoping that you can share this with people. Give it a shot. Try the speed of light normalized to 2.99 and tell me that that residual doesn't start resembling root 2. I want to see if the audience can actually engage with this and find their own structures, and let's connect. Let's find a way to get this to the mathematical community and share this ideas, because I think there's something novel and very unifying here. Ladies and gentlemen, thank you so much for this long episode. I know it's a lot, but at the same time, it's kind of big, I think. These ideas are worth sharing, they're worth considering. And if you stayed this long, then yeah, I just want to give you my wholehearted thank you. And for the next episode, I will be working on how to create palindromes with the exact same structure, as well as being able to calculate pi from prime numbers itself. Thanks for joining me, ladies and gentlemen. This is Felipe speaking, signing out.